Hello and welcome to my Graphics Semester 2 video. This semester covers terrain and animation. For terrain, we have various 2D and 3D techniques that can be accessed from this create menu. The first technique is loading a height map. You can browse for the height map in here, and we have several to choose from, or we can load a preset like default height map. Once we've got our height map, we can click OK, and it will generate. Here is the loaded preset with the terrain shader on. This is a good one to show off some of the available settings. So by default, the height map is loaded, and we can change the scale of the shader by adjusting this max height value on the side. By default it's locked, which uses the height of the height map to adjust it. You can also change this value called steepness threshold, which affects the normal values. So if it's really high, any shallow kind of terrain will be just blended. The lower it gets, any steep terrain will blend to grey, giving more detail to steep surfaces. The terrain can be generated at any size, but with height maps you want it to match the image. You can be regenerated if you change any of the settings by clicking the generate button. You can also view the terrain in wireframe mode, which shows the actual plane mesh and how it has been deformed to make the terrain cosmically invisible. And if we were to create a ocean object, which we can do by going custom mesh plane, and we create a plane with 512 as the default, and we make it translucent, and we change this to be there. We now have an ocean plane which is translucent, which allows us to see under the water with a flat surface. This works best when there is lighting enabled, so if we enable lighting on both models, it will initially be black because we have no lights in the scene. If we now add a light to the scene, such as a point light, OK, and a point light will be made. Now, at the moment, the point light is very small, so we need to adjust its settings to provide less effect, or less attenuation, which would provide a greater radius of effect. Move it closer to the surface, and there we go. We can see that the terrain is lit accordingly, and the surface reflects the light like as a point, but also the terrain beneath the water is also lit. We can also have two different modes of lighting, or at least shading. So if we select the terrain again, we can regenerate but with flat shaded. This will, instead of having blended vertices where it uses indices, every polygon has its own set of vertices, causing the effect to be flat shaded for every polygon, which looks like this. This makes it a lot clearer where the plane is, and if I move the terrain up and down, you can see that the water level dynamically adjusts to match the plane, which is at 0, and you can see how the lighting affects that. If we move the light around, you can see that the lighting works the same way, but applies to the whole polygon instead of a smooth transition. Okay, now I'm just going to clear all of the objects, including the ocean, and move on to the next generation technique. So next one is the first procedural technique, which is fault line. If we load the preset fault line and click OK, it will generate some random terrain. Now, as you can see, it's currently very flat. This is because we need some scale to the terrain. If we set the scale of the object to 1 and the generation scale to 1 and generate, we can see we have some terrain. Now, fault line terrain is not the most realistic, especially at this low number iteration count. It's very clear where the lines are drawn, but if I increase the generation count tenfold to 1000 and regenerate, we can see that we have a lot steeper terrain. I'm just going to regenerate with a lower height value to make it clearer I adjust, this is quite a macro scale, so there's lots of big mountains and stuff, but it's a lot less clear where the lines are. Again, you can see the wireframe mode. This is a lot smaller of a plane than the height map required. All of these support the same lighting situations. I can also turn off randomness, which will generate the same lines each time, which is useful. So if I reduce the number of lines to 10, we can change this to 1. You can see that these are the lines, the first 10 lines. As I increase to 100, terrain will start to form. You can see that it's clearly divided into kind of two halves at this point. Mountains on the left, water on the right. And as we reach the 1000 mark, the terrain has become a lot different. This uses the same seed for every single one, but more iterations means more randomness. This can again be applied to all of the techniques. We now create a next one. The next terrain generation technique is circles, sometimes called hills. Again, load the preset and click OK. And here we have some terrain generated with 1000 circles of varying radiuses. It's a lot more cartoony than the previous one, although there are still some peaks. And the larger the radius used, the more it will generate these kind of edges that drop down. If anything, it's the whole terrain rising up. The smaller, if the radius is smaller, this effect is less. The next terrain is the particle deposition. Now there's two modes for this, which I've got saved here. There's the roll mode, where particles can roll if the steepness threshold is met, or there is the sticky mode. First, the roll mode. This is using 10,000 particles across 10 different points, so that's a total of 100,000 particles. And the roll mode with a threshold of 5 is pretty macro scale as a terrain generation technique, but it's also not exactly clear that it was made with an algorithm, so it's got its benefits. The sticky mode, if I delete this object and create a new one with the sticky preset, which is this one, and click OK. It looks very similar, but you'll notice that the peaks are a lot sharper. This is because there's less smoothing going on naturally with the rolling than with the rolling one. Having a roll threshold that is super high will also increase the spikiness of the rolling method. Okay, the last 2D technique is diamond square. Now this, unlike the others, is based on the number of iterations, which we will be using 10, which takes a little while to calculate, but it is worth it for the final result. Here we go. So this is the final terrain. It's quite a bit bigger than the previous ones. This is actually 4 times bigger than the original height map one, which took a while to generate. But it kind of gives the most realistic looking terrain of all of them. If I increase or decrease this, you can see how complex the mesh is at the boundaries, and if I wanted less water, I could have bigger mountains, or I could have just a small island with a really deep ocean in between. But usually the default is about right for this. And this is it needs a smoothing pass really. There's a few spikes at the midpoints, but it's probably the most realistic of the implemented techniques. So if we do that, we can move on to 3D techniques. For 3D, we have 2 options. There's just voxels, or voxels, and marching cubes. The first one is the voxels, which we will load as so. This uses a combination of the previous fault line technique along with some 3-dimensional Perlin noise to generate caves and tunnels. And as you can see, it has overhangs in the terrain and makes full use of the 3D nature. This is quite small, so we can increase the size and regenerate. Can we change this to regenerate? Here we go. As you can see, this terrain is not exactly realistic. There's lots of big holes, but the principle is there. It uses the voxel kind of rendering, 1 cube per voxel. If it's solid, it's a cube. If not, it's not. And there is an optimization, so if I switch to wireframe mode, you can see that there are no internal vertices or faces. It is only the outer edges, which makes it a lot easier to perform, although it does take longer to generate. Okay, the final 3D one is the same generation technique, but a different way of calculating the bounding mesh using marching cubes. It uses the same preset as the previous one, but I will also increase its width and depth again. Here we go. As you can see, the mesh for this is a lot smoother, although it does have some strange artifacts due to the complex nature of the cloud of points, the voxels that make it up, but it does provide overhangs in the terrain. To make this really good, you need a system for ensuring that everything is enclosed, like in the static cloud, as opposed to like the rifts that happen at the moment, but the principle works. And if I go to wireframe mode, you can see that the mesh is a lot more complicated than the voxel one, with like smooth transitions around corners, which if I switch out to wireframe mode are visible like here. Yes. Okay, now we'll move on to tessellation. So first off, a tessellated plane with just the one cell. We will zoom in a bit, and we can see it's better in wireframe mode that this currently has a tessellation value, black, of 2, tessellation factor of 2. If I decrease, we have just the one cell. This is like the plane that was generated before, and as I increase this tessellation factor, you can see that it tessellates like a fixed amount throughout. Now if I increase the size of the plane to 10 by 10 cells, currently it will work the same way, where it tessellates the entire plane. However, there is this dynamic mode. Now this uses the position of the camera to dynamically tessellate the plane. So as I go in and out, the plane tessellates around up to a maximum amount, which is configurable over on the side. If I reduce the threshold, it reduces or increases the amount of distance that the camera has to be away before it starts tessellating. So a low value will only tessellate up really close, and a high value will tessellate when you are much further away. There is obviously a certain point where the tessellation is unnecessary, which is why you can change the max tessellation factor. So here it will only tessellate up to this point, so there's a lot less of a transition. If I move on, we have a more complicated version of this, which is a tessellated height map. This works the same way as the main height map, but uses tessellation. So to begin with, we'll have a width and height of 1, and use this height PNG. No. This uses the same height map we had loaded earlier, but there's only one by one cell. However, as I increase the tessellation factor and reduce the height of the mesh slightly, we can see that the terrain ends up looking pretty similar to the initial height map. For reference, I will load in an object of the height map so that we can compare. So here we have the full-scale terrain. I'll just move that over to the side. It's obviously a lot bigger than the tiny terrain height map. So if I scale this up by 100, make this one 20, and this one 100, we can see that it has the exact same shape, although it is at a much smaller scale, and the normals are a lot greater because if at the full calculation size, the heights are a lot more extravagant. This is due to the way the height scale that was used to generate. If I was to reduce the height scale, you can see that the height scale is now a lot more reasonable, although the actual max height scale still needs adjusting manually. If this is all from the single cell, so if I reduce the tessellation factor and go into wireframe mode, this is all from this one cell. As I increase the tessellation factor, you can see the terrain emerge. So at a halfway point, the terrain still looks pretty reasonable, and it's only when you get to very low tessellation factors that you lose any significant amount of detail. However, the fixed step means that we can, the dynamic mode even lets us tessellate as we get closer to the camera. So currently the plane itself is not tessellating. If we increase the threshold dramatically, we can see that the plane tessellates as we get closer. Without wireframe mode, this gives the effect of, as we get closer, the terrain coming into focus. The current issue with this is obviously that the whole point is that we are further away. If we increase the tessellation factor a lot, we can see that we have to be further away before we lose detail, and by the time we get close, it has gained almost all of its detail. This tessellation obviously works better the higher the visual plane size is. So if I just recreate this plane for simplicity's sake, okay, we can see that we have a 10 by 10 plane here, so in wireframe mode at the fixed one, this is what the base looks like. So there is still a slight change in the mesh from the height map, but as we increase the fixed step, we get even more detail than before. Again, there's the large version to compare. If I increase the height scale, decrease the height scale, and change the steepness threshold, we can again affect the grey colouring. And if I switch to the dynamic mode, because we have a higher base resolution, the resolution of the tessellation doesn't need to be as high to get the same amount of detail. So as we get closer, the detail gets a lot more intense. We can obviously keep going with this, where we have up to 100 by 100 cells, and regenerate. The base cells is now a lot larger, and as if I increase and decrease, you can see the tessellation wave go across the object. And this obviously applies a lot closer as well if I increase the height scale of the mesh and change this to an appropriate value and this to an appropriate value. If I now change the tessellation factor, you can see the detail around the borders of the water, and if I get a little closer and reduce it, you can see it up close. Obviously I can also reduce the max tessellation, but because we have such a high detail plane, it's mostly similar to the large version. Okay, that does it for the terrain demo. The next section is about the animation. So we will load a scene that contains a humanoid character. Here we have a Viking, and we can see he has bones. Each of these blue objects here is a bone. The shape is used to identify the direction of the orientation. I can scale the bones so that they're not as obtrusive. We can expand this tree on the right here to show all of the bones in the model, of which there are a fair number. And if we select one, it will be highlighted yellow. Now it is possible to manually manipulate this mesh, and as you can see, the mesh is skinned, so it changes to the bone structure, change the mesh, and we can reset the bind pose. So for example, if I select the left shoulder over here and move it to the side, not like that, if I move it to the side with this one, it is quite dramatic. It's better to use this for positioning. The reason for this is because this bone is orientated, and so the gizmo doesn't align, and therefore causes slight issues when it's not aligned. But the actual position changes still make sense. So there we go, and we can move, and obviously it's stretched his arm in a way that shouldn't work. Now, if we were to select the root again, we can also rotate, so we can rotate the entire object just by changing the bone structure. This isn't the actual game object, so if we were to select his spine, for example, we could rotate only his top half all the way around, or we can reset. So that's the bones. Now the animation, we have a short animation playing. He's slightly larger, and if I loop the animation, it's a little bit clearer. We can also hide the bones to make it clearer, and at the moment the animation is playing at its default speed, and there we go. He has several different poses at the end. If we slow the animation down, we can get more detail on, say, the run. So there you go, and if I show the bones again, we can see that the bones move with the animation, causing the skinning to move too. And there we go. You can have multiple animations on the same object, but this one just has the one. It just has the one main mesh as well. And as the bones are moving, if we carry on playing, we can actually select one of these moving bones. This hip bone here, which is the root bone of the main skeleton. You can see the positions change, especially if I increase the speed again. You can see that when it switches to the more extravagant one, the movement is a lot bigger. This is the rotation matrix, and this is the offset matrix. You can change all of the settings from within here using the gizmo.